Okie doke. Well, let's go ahead and get started then. So thank you for coming this morning to the Launchpad Lecture Series. I am still Chris Orwoll, the director here at the museum. Nice to see a nice large crowd here. Hopefully I'll give you some information that you don't know. As usual with these lectures, I'm pretty sure that at least a few of you out there know a heck of a lot more about this subject than I do. So, but in any case, what we're talking about today is going to be crowded skies, orbital debris. We just did the new satellite gallery in the museum. We opened that up in March, and part of the satellite gallery for us is a little section on crowded skies at the end. Additionally, we're currently working with White Sands Test Facility on doing a new exhibit for them that's going to go into their headquarters building and out at a place called the Remote Hypervelocity Test Laboratory. I'll talk more about that in a second. And that portions of that exhibit will come into our museum as well. So it's kind of a neat little connection and why we're talking about this subject. So in any case, as part of introduction, basically I grew up in Downey, and I always put this because I'm never sure who's new in the audience. So grew up in Downey where they built the Apollo command module and the space shuttle. Nobody in my family on my side was directly related to it, but on my wife's side, her father actually worked on both of those programs as well. My mom would take me out to when the astronauts would come back from the Apollo missions. That is actually me right there, having just shaken John Young's hand. So after that, went to the Naval Academy, graduated in 1986, drove these around for a number of years, retired in 2006, ended up running a museum in Kansas, did that for almost 6 years, and then came down here. There's my family a number of years ago, considering that this little guy here is well into his teens, and is coming into the last part of his high school years. But I use this picture because, yes, I sent them to space. Up in the cupola window. And we'll mention the cupola window during this lecture. Space isn't empty, it's crowded. We think of space as being extremely vast, but in the areas that we're talking about, when we're talking about crowded skies, we're talking about the Earth orbit areas, so the area around Earth. So similar to, New Mexico, not a lot of people. Let's take a look at our county, so just over 60,000 people in a county that's bigger than the state of Connecticut. But if you go to Connecticut, it's a little bit more crowded, and the roads are a lot more crowded, et cetera, et cetera. You're much more likely to get into an accident of some sort, which is the concern that we've got as well. So this is one of the, still shots showing satellites around the Earth, quite a few, but you'll see here. What is that made up of? Well, things as small as, say, a Vanguard satellite here. That's going to be, that was launched back in the early days of our space program back in the 50s. It's going to be up there for well over another 200 years based on where its orbit is located. Spent rocket bodies that are out there, maybe a shuttle blanket, thermal blanket that came off during one of the missions, paint flecks, pieces of exploded rockets, because when we launch stuff into space, traditionally, they left a lot of fuel in the upper stages of the rockets, and then space is a harsh environment. Those things eventually, quite frequently, exploded. When they did, a lot of space debris was created. So, such to the point you're talking about things that are greater than 10 centimeters, there's over 25,000 of them up there. Things that are between 1 and 10 centimeters, there's over 500,000 of them up there. Things that are greater than 1 millimeter, you're talking over 100 million things that size. In 2022, which was the last estimate I saw, there's 9,000 metric tons of material orbiting the Earth. So that's a lot of stuff up there that could create problems. In any case, though, this is just kind of zooming in. Obviously, this is stuff that's in orbit, so with the larger ring out here being the geostationary orbits. This is very obviously Earth right here. That just gives you an idea of all the stuff that's out there. And for we live in New Mexico, so if you go out before sunrise, after sunset, you're going to see satellites flying over. You just have to sit there and stare at the sky for a little while, and you're going to see satellites going over. So this is the locations where the objects are. So the density, the number of objects. So, and then this is the distance out from Earth. So kind of 750 kilometers to 1,000 kilometers is where the majority of stuff is. And then you got stuff out here in geostationary orbit as well. 1960, 1965, 1970, 75. You can see the huge growth here. 85. We're up into the 2000s now. And it's just continuing to grow. So this graph really is taking a look. So back here, very obviously, we just started launching into space back there in the 1950s with Sputnik. And then it was just kind of a linear growth. And then you see a couple of big jumps here in the 2007 and 2009 timeframe. Does anybody know what those are? These big jumps right here? Nope, nope. SpaceX is the cause of this over here. Really. So this one right here, sorry, did somebody say something? GPS? No. Actually, it was an incident, 2 incidents. The first one was a Chinese anti-satellite test that was in 2007, and you can see that huge jump. And then you get another big jump here. That was when a Russian Cosmos satellite accidentally, not an anti-satellite test, but an accidental, collided with an active Iridium satellite. So it was a defunct Russian satellite that collided with an active Iridium satellite. And so you had these 2 collisions here. That actually makes up about 1/3 of the space debris now. Those 2 incidents. So, what's that? Us. Iridium is the satellite phone system. So SATCOM essentially. So, and then you see this kind of almost exponential increase down here. What does that do to these babies? Starlink. So that's going up there. So over 6,000 satellites now. They're planned to get up to about 12,000 satellites. They're small. They shoot up in banks like this. And if you've looked up at night, sometimes right after they launch, you'll see a train of satellites, essentially satellite, following along until they get into their new orbits. These ones are about average, about 650 kilometers up is where they're located. So, and this is just the Starlink satellites. So, new small communication satellites, and that's just the first. There's going to be more constellations like that going up. Amazon has one planned, the Russians have one planned, etc. So it's going to get more and more crowded with these little objects, and at some point in time, things could go wrong. So the Orbital Debris Program Office, which you saw the logo for up there a little bit, is part of NASA. They're the main folks that really take a look at this issue. And some of the things that they do, I'm going to kind of cover them here as we go through. So modeling. So they're modeling what is the environment going to look like. So you see that it goes up to now when you're looking in here. So, and this is, you can see the projection with explosions, 90% or more with explosions than without explosions, etc. That would be like if there's collisions going on. So, and you can see here that it gets a little bit crazy as far as the number of objects going from about 12,000 here up to over 55,000. At some point in time, there's an issue called the Kessler syndrome. So the guy who was in charge of this Orbital Debris Program Office, and the one who started it up actually back in the late 1970s, Don Kessler, NASA scientist, he's now retired. In any case though, he had actually started working and taking a look at the thing that was a big issue for us when we were flying in space back in the 50s, 60s, and 70s, which was essentially micrometeoroids impacting with the spacecraft. So pieces of the meteor belt with things that interact out there. There's a lot of objects out in the asteroid belt, and those things will collide with each other. Little bits will shoot off, and some of them will come down. They'll impact our spacecraft. Still happens nowadays. In any case, though, he was studying the frequency, he was studying the chances of impacts, etc. And then as space became more crowded, you saw the progression there in the video that I was showing. It became more of an issue of things that were up there that we put up there. Because when we were launching upper stages back in those days, or launching rockets up and things like upper stages would explode, that was the vast majority then of the debris that was created, was from those things. But you saw based on the anti-satellite test that the Chinese did and the collision between the Cosmos and the Iridium satellite, you can have huge jumps in the amount of debris up there when you have collisions of some sort. Just recently here in the last couple of years, we had a satellite get knocked out by a small piece of debris hitting it as well. So it can happen and is happening. The Kessler syndrome is that one that postulates you get to a certain point and you will have had enough collisions that create enough debris that create more collisions, more debris, and it takes off and it's unstoppable. And then you have Gravity, the movie. That idea of basically you have so much debris in the areas that you want to be flying in, especially low Earth orbit, where we want to have things like communication satellites and things like that. In any case, that it makes those areas of space unusable, or at least extremely expensive and difficult to use. So they have to, NASA really takes a look, and actually NASA, ESA, Russian Space Agency, et cetera, are all kind of working on this and taking a look at it. So they do a lot of modeling on it. So measurements, they're actually measuring what's up there. I gave you some numbers just a little while ago. Where did those come from? Well, if you take a look up here, so they take a look at spacecraft and other things. So when the shuttles came back, when they brought back pieces of other spacecraft, Solar Max and things like that, they took a look at it and they would see what sort of impacts were on there. Every time that a shuttle came back, virtually every time, they needed to replace some windows because there would be impacts in the windows. And the astronauts will tell you that if you get an impact from something hitting, say the space station or a shuttle, you can actually hear it. You'll hear that on the outside of the spacecraft. Slightly frightening sound, I would think, in any case though. But then, so not only do you inspect what's actually been up there, and you're taking a look at the hits that you get in that one. Obviously, if you had a huge hit, that's why you see that it's pretty small, the size of the impacts right here. If you had something large hit those spacecraft, it wouldn't be coming back. In any case, though, so for the larger stuff, Goldstone radars, Haystack radar, the Haystack Auxiliary radar, U.S. Air Force's Space Surveillance Network. So here's what some of those things look like. Goldstone orbital debris radar here. So 70-meter dish, so you can see cars here. Pretty large dish out there. Low Earth orbit down to 2 millimeters. And you can see the statistics up there. These are the Haystack and the Haystack Auxiliary radars. These are up in New England. So primary source for 5 millimeter to 30 centimeter debris. ESA's got space debris telescopes. So this is over in Germany. So I'm just going to kind of run through these ones. This one's up in Alaska. Phased array radars. Phased arrays radars are the same ones that we utilize on some of the Navy ships. Now the destroyers and the cruisers that we had. We use phased array radars on it. And the statement was, even when they came out back in the 1980s, you could track a basketball around the moon. They're a lot better than that now. A lot better. Another phased array radar here out at Eglin. So the Keenan reentry measurements, this is out at Kwajalein. When we launch missiles, either for a ballistic missile land-launched or sea-based launched test, they'll fly over to Kwajalein, and that's where they'll land. These are the radars that track them. We also use them to track deep space objects. So then there's other ways. We will send up spacecraft that we then utilize to test and see impacts on it. So one of them here, the Long Duration Exposure Facility, that was taken up on STS-41C back in 1984. It stayed up there for almost 6 years. And then it was brought back. And you can kind of see here, it doesn't look as good. So in any case, and it was up in a 257-mile circular orbit. We sent this up to kind of test out different materials, see how they survive in the long duration space environment, as well as impacts. So not just solar radiation and issues like that, but also impacts. And it was in preparation for Freedom, the space station that was going to be a US space station. Eventually, the concept gets turned into the International Space Station. The other one, another one, Explorer 46, back in 1972. Re-entered in 1979, but it did its testing mostly in that 1972 timeframe. This is actually on display in the museum. And you can see it up there. The interesting thing about it, you look at it right here and you see these gigantic sails sticking out. those are located right here. So if you're up in the museum, this looks like a roll of Reynolds wrap, aluminum foil, right there. And then this whole section would extend out like that. And then they could measure the number of impacts that occurred on it. So 20 meteorite and 2,000 micrometeorite hits just from August to December of that time frame. Quite a few. So these are some pictures of the space shuttle from different missions, 123, 122, 130, etc. So obviously a little bit bigger on our screen. You can see the sizes of them here, you know, so 4 millimeter. Is the size of that impact. One of the neatest displays that I saw was when I was in the building where they prep the shuttles prior to flight. When they bring them back, they put them in there, the shuttle processing facilities, and then they prep them up for the next mission. They'll take a look at all the tiles, they'll make all the changes necessary, refurbishment. They had on display in there one of the shuttle windows, and it had blue lights all around the outside edge, and you could see some of these dings in the window, and it was kind of sobering to understand that, yep, even if it, you know, if it just goes up on 1 or 2 missions, that it does get hit. We know they're going to get hit. We measure how much material is up there. Statistically, we know there's going to be impacts. So what do? You protect the spacecraft. So the Orbital Debris Program Office works on ways to protect the spacecraft. How are you going to do that? Well, kind of, by the way, there's a ding in the window, and that's on the cupola window on the space station. So where there was an impact. Shielding. So you can do different types of shielding, but this is a post-flight inspection of one of the shields, and you can see all the places where there were impacts in this. All these little markers are showing where there was an impact in it. So, but this was part of the shielding on the spacecraft. Why are we concerned with protecting? Well, very obviously, you don't want the stuff to impact on the inside, but even when it impacts on the outside of the space station, it can cause these impact points, and I'll show you a vivid example. Actually, it'll probably be easier to see with this one. This was a hypervelocity impact into a Whipple shield, and I'll explain those here in a bit, but you can see, you know, kind of how everything is blown out from it. So the astronauts, when they go around the space station, have handholds. And if you have a handhold that's had a micrometeorite impact onto it, and it creates something like that, and you grab it with your glove, what could happen to it? Rip your glove open. The outer layer is just an annoyance. If it rips the inner layer, that's a bad day. That's a very bad day, because essentially your portable spacecraft has just been destroyed. And you are not going to survive. And yes, they have had incidents with the astronauts getting their gloves, not the inner layers, thank God, but the outer layers damaged. So they're very careful about, you know, you wonder why you see astronauts moving slowly around the space stations, because they're looking at everything and seeing if there's something that could endanger them on the outside of the spacecraft. And it's the reason that the spacecraft does get inspected, or the station does get inspected quite frequently, all the areas that they're going to as well. So we have to figure out how to protect them from things like that, inspecting the windows, the shields. This was Mir. It's a little tough to tell in this image, but you can see all sorts of dings in it. Mir was a space station before the ISS, and it took a lot of hits, especially on the solar arrays that were sticking out here. I apologize, it's not as easy to see here as it was on my computer screen. With the testing and trying to figure out different types of shielding that work for the spacecraft, one of the primary places that they test different types of shielding, different types of spacesuit materials that might be able to provide more protection, etc. Different ways of building things like tanks, batteries, trying to figure out if they have an impact that hits an external tank, or it hits something electrical, or it hits something toxic. What might happen is the Remote Hypervelocity Test Laboratory. That's located over at White Sands Test Facility, just on the other side of the mountains. This is the inside of the test laboratory. They've got 3 guns in here, a 1-inch, a 50 cal, and a 17 cal caliber. They're 2-stage guns. The first stage of it is smokeless powder that they utilize that explodes a sabot round that is a polyethylene round with a little pellet on the inside, and they can vary the size of the pellet up to almost 1 inch. It's got the sabot inside of it, so that will shoot down here, and it shoots the smokeless powder with the sabot that then compresses hydrogen. And the hydrogen gets extremely compressed behind that, and then there's essentially like a burst disk at the other end, and it will release that pressure, and it will shoot it up, and it can get things going up to 5-6 kilometers per second shooting in there. Stuff flying around in space, the debris that we see flying around up there, so is generally going around 7 to 8 kilometers per second. And then if they have the average impact speed that they're able to calculate based on the types of impacts they have is about 10 kilometers per second. But you could have up to a 15 kilometer per second, and it's all about geometry. You know, so is the thing hitting like this, or is it striking like this? You know, if two things are traveling 7 to 8 kilometers per second and they hit head on, that's a 15 kilometer per second impact. So in any case, inside the lab, they then have these chambers that down here that they evacuate everything out of, and then they have high-speed cameras there that can record up to 2 million frames per second. So there's kind of what a sabot round looks like, and this is the 1-inch gun right here. And they shoot these up to about 600 times per year. So that's how frequently they're doing tests inside the lab. So, remote hypervelocity test laboratory. So what have you got? This is the White Sands test facility. These are the main areas. The headquarters is right down here in this area. Oops, excuse me, in this area right here. The remote hypervelocity test lab is out here, kind of far away from everything else, for very obvious reasons. You're shooting stuff at extreme velocity, and you're shooting things that might not react too well, because they have the capability of shooting not just at a metal shielding plate like this, or like the other one that I showed you. They have the capability of shooting at batteries that are energized, tanks that are pressurized, tanks that have toxic materials in them, all those sort of things. There's bunkers down underneath the laboratory for the personnel when they're doing the tests as well. So that's kind of that just in case something happens. So it's out a little bit further away from everything, so it almost feels a little bit odd to drive this road along here and then up to the actual lab itself. And there is the laboratory, the building that I was just showing you the interior of. So this is what an impact can look like with an object coming in, and that's a fairly, you can see there's a quarter right there, so this is a fairly thick chunk of metal. And basically it's the same when you have meteors that hit the moon or the earth, something like that. Those are hypervelocity impacts. And so craters on the moon, this is essentially the same thing as like a crater on the moon, except for in this situation it went completely through. You saw a very thick piece of metal there where you can shoot something at it, and here I have two pieces of material, one fairly thick and very solid, heavier too. So this is about, you know, this is over 1.5 pounds of material right here. And then you can see the impact that was right here. It did not get through, okay, so you stopped it, but it's heavy. Or you can use something like a Whipple shield, which is what one of these are. So, which basically, you have the impact point right here, and then as it hits that thin material here, which can be made up of a whole bunch of different things, this basically is a sandwich material that has a composite on the inside. You could have it where it's just metal, like this one. But if you get the penetration through the first one, everything spreads out as it goes through the first one. And hopefully your second or third or fourth shield will protect it. This is essentially how the International Space Station, in the areas that you have to protect more, where the people live, where maybe there are tanks or batteries, things like that, they have types of Whipple shields around them, which is layers of shielding, so that hopefully if something hits it, it will get stopped. If it goes, 1, 2, 3, 4 layers, like you can see in the upper image there, you can see where you had something go in, and then it subsequently, as it went through each layer, it got spread out more and more. Another example with the different types of materials. So the Orbital Debris Program Office also looking at mitigation, remediation, and re-entry. And I kind of lumped all these ones together, even though they list them out separately. So what are we talking about? It was another video. I'm going to skip it just because we had problems with the other one. So that video, though, was the clip from Pirates of the Caribbean, where he talks about, the rules of parlay, and he says, they're more like guidelines, actually. And in this situation, there are no laws about mitigation of space debris and things that they require countries or companies to do to try and limit the amount of space debris from objects that they launch up into space. There are guidelines, but everybody follows them for the most part. And are other countries, do they have guidelines as well? Yes. Yes, they do. Yes, Russia, China, European Space Agency, French, Japanese space agencies, etc. Everybody understands this problem now and is trying to help mitigate it. So what are some of the things that you can do? Well, you can try and remove stuff. That's the next up and coming thing, is that not only do you try to limit the amount of stuff that gets left up in space, I'll talk about that in a second, but for the stuff that's already there, especially the big objects, that's what's most concerning. That's what Kessler, really wanted to try and take care of about, 500 objects in the next 100 years, and bring them down, the large ones, to try and mitigate the possibilities of that incident, because it's really the collision of large objects against each other that creates the biggest problem with that potential cascade. So in any case, next year, hopefully, the European Space Agency with a Swiss company called ClearSpace will launch ClearSpace 1. That will go up and will actually grab a hold of this portion right here of the Vespa. It's part of the upper stage. It's one of the adapters in the upper stage, and it's going to try and grab this this object that weighs 112 kilograms, and then and its orbit is elliptical. That's why it's the 664 to 801 kilometers there. And basically bring it back down. And you don't just fire the rockets and shoot it back down suddenly. You got to bring it down slowly in stages, especially just to make sure that you don't hit anything else on the way down, bringing it back in. So we'll see how that works. So the ESA is working on that one. Another one, Astroscale. This is one where they're working with the Eutelsat OneWeb, who's partially funding this. The UK Space Agency, the European Space Agency are working on this as well. 2026, they're going to try and go up and grab a hold of one of the small satellites. And they do this with magnets. So basically the idea is, if this works, the idea is that you launch your spacecraft up and it has one of these magnets attached to it. It's sort of like the magnet on the back of your phone that you might have that you can attach to things. And they'll send up this small satellite that will essentially grab onto it with the magnets and then do the same thing. Bring it down, bring it back down. So it will help for future launches. This is one that's been in the news here recently. So this is coming at some point in time. What's the largest object up in space right now? Besides the planets and stuff like that. But the largest man-made object? International Space Station. NASA's plan is not for it to be up there permanently. Their plan is to bring it back down in 2030, and the contract was just let out to SpaceX to basically design and then eventually build a large version, essentially, of the Dragon spacecraft to go up there, dock to the International Space Station, and then bring it back down and deorbit it and bring it back down to Earth. Other space stations have come back down to Earth in the past. Sometimes controlled, sometimes a little bit more uncontrolled. So for those of us old enough, we may remember Skylab. And when it came back down, pieces of it landed on what country? Australia. So in any case, that's not where you want things to land. And I'll talk about that here in a second as well. So they take a look at the re-entry risk as well. They also do modeling of the re-entry risk of satellites coming back and re-entering. And the concerns there are, well, very obviously small satellites or things like the solar panels and things like that. Stuff's going to burn up on re-entry. Up to a certain size, weight, thickness, etc., things are going to burn up on re-entry, coming back into the Earth's atmosphere. But when you get above that size, things can make it through through that re-entry process and land here on Earth. Sort of like that. Right there. So here is, so breakup normally occurs between 84 and 72 kilometers high. That's when satellites really kind of break up. The nominal breakup point is 78 kilometers. Solar arrays tend to start going at about 90 to 95 kilometers up because they're thin and not that much to it. So aluminum is a lower temperature. So things that are made of aluminum are going to burn up a lot easier, but things that are made of titanium, stainless steel, beryllium, carbon-carbon composites, things like that, much higher, so they're more likely to come in. So your spacecraft design can take those things into account for when you eventually re-enter these spacecraft and how likely are you to have something come all the way through. SpaceX, for their launches, they've had some landings on land. So they're actually moving their re-entries to the Pacific Ocean from the Atlantic Ocean to try and limit the amount of debris coming down on land. And it should, since everything should land over the Pacific Ocean. So, and then NASA does a couple of different modeling methods, and these are the two listed out there that they utilize. This one's a higher fidelity modeling. So where do you want to land things? Well, if you can't, normally we're used to looking at a globe, and we're used to looking at either like the northern hemisphere, or North America, Central and South America, or Europe and Africa, or Asia, or something like that. This is really where you want to bring things down, because if you looked at Earth from this vantage point, you mightn't think that there was no land here on this planet. So, because 70% of the Earth is covered by water, who knows where this is? South Pacific. There's New Zealand right there, Australia right there, and there's North America right there, Hawaii. So this is where you tend to bring stuff down, or you try to. So that's where a lot of that modeling, those re-entry models that were on the previous slide, that's what they utilize to figure out when the satellites are coming down, where might they come down. So they know what the orbits are, they know what their altitude is, they know how much that altitude is changing. Those different models can predict how quickly they will or will not come down. And we've got a lot of experience now with these things coming down. Natural re-entry, obviously artificial re-entry, etc. So what goes up doesn't necessarily come down. That's kind of a discussion of the issues of it. So one more thing. I always have that up there. I will have these two pieces of material available back in the back after the lecture. One thing that I will say is feel free to take a look at them, but don't pick them up. And the only reason I say that is because this is sharp. There's very sharp edges to the Whipple shield and to this, right where the impact point is. So I just ask that you don't actually touch them while they're up there. But you can get a couple of ideas of what these materials look like. So what? What questions do you all have? And we could probably bring up the house lights. Yes. It's not willy-nilly. When they're launching up and their launch trajectories, they do calculate out and try and figure out what else could potentially be. Most everything is going the same direction. So you do have polar orbits, you do have, so most everything is going the same direction. So yeah, kind of works a little bit like a freeway in space, but you saw also that there were things going all different directions. So they work on trying to put these things into orbits that will not interfere. And you don't have to, it's like two planes can fly like this and never interact. Two cars can drive like this and never interact. It's where you got this, where you have the problem kind of thing. So they will try and do, and very obviously, since it, I'm going to knock on wood, but it has not happened that frequently of these collisions, so most of the issue to date has been due to not where people have purposely put things, but because something else exploded, or there, and that, like I said, the upper stages. So one of the other things, like I said, with mitigation, I did forget to mention this, I'm sorry. So basically nowadays, when they launch up satellites, they have to have a plan for deorbiting them after they've been up there for a certain amount of time, their lifespan plus X number of years. And so that is one of the things that they have to have a plan for figuring out how to bring it back down. For the upper stages, they'll try and limit the amount of fuel that they put into it so that you don't have these explosions of the upper stages, which they used to have when they just overloaded the rockets with extra fuel and things like that. So there's a number of things that are done nowadays, the materials that they make, the rockets and the bodies out of, the way that they do batteries, everything, to try and limit the amount of debris that gets created from things that are unplanned, so that's kind of how things are done. But as far as putting things in orbit, yeah, there's models of all the large stuff, And so you put your orbit up and you plan it such that you won't be interacting with anything else. So yeah, it's not quite like everything's in the same lane though. So the question was, why don't you put the bigger objects further out into space? The different types of satellites that we put up into space need to be at different altitudes for the mission that they're doing. So like communications, all the, whether it might be a Starlink satellite or something, you want it lower down. Like the Starlink satellites are put at a certain altitude and it's a little bit lower down so that they have less latency. That means the speed that the information goes up and comes back down. So where they put the objects depends on what it needs to do. So the area that's most crowded is lower Earth orbit, that lower area. And then we do have objects that are obvious, that are much further out as well. One of the things for the, another way of mitigating the issue, when you get a satellite or something that gets to the end of its life, you can actually put it out essentially in a deep orbit where there's nothing else out there that you're worried about. So it's a parking orbit, and they will just put stuff. So that's one of the mitigation things as well nowadays, is that you either put it out far enough that it will not interact with anything else, or you bring it in close enough to Earth that it will deorbit in a much quicker period of time. But it really depends on what the spacecraft is going to be doing, and that's what drives where it goes. Not you try to put it in a less populated area of space, but can't guarantee that if your mission is that you need to photograph something, or you use your radars or communications or whatever is the purpose of the satellite. So it's an interesting point of, by the way, the US has done an anti-satellite test as well, and did that, but for the way that they did it, NASA told the military not to do it. The military did it anyways to prove they could do it, and they did it, and it created some debris, but nothing like what happened with the collision of the Cosmos and the Iridium and the Chinese anti-satellite test. In any case, though, yes, I mean, the capability exists to knock out any satellite. We have it, the Russians have it, the Chinese have it. So that does exist, so it could. But if we start doing that, and that's one of the U.S. Space Force. It's one of the things that they're taking a look at is what could happen to our satellites, what could be done to their satellites, how could they be taken out, So is the idea maybe that you send up a satellite that just lasers, another satellite and takes it out that way by destroying some of its capability. Because if you start doing the explosions, you're putting your own stuff in danger as well, because you create that situation where eventually it becomes untenable. Launching something up to grab somebody else's, they're going to watch that the entire time. It's not like we don't watch. No, everybody's tracking everybody else. Yeah, so. Yeah, and a nuke out there would be really bad. So, yeah. Well, we've got them parked. We've got them parked all over the place. So, yeah. So, if we're doing it, we know that, the Russians are doing, as far as Intel satellites, a lot of nations have got them up there. We have a whole constellation of them, so. Nope. Not without creating a massive international war-causing incident. So, yep. Yeah, the satellite, the Chinese have some issues with their launches as well, and debris and things like that. So they have not only an issue with debris in space that they're trying to limit, but they have issues with debris landing on land from the satellite or from the rocket launches as well, which has been interesting to watch over the last bunch of years. There's lots of video out on the web of rockets coming back down and crashing near villages in China. So kind of scary, especially when you think of the chemicals that are in those rockets. Well, we like having things like GPS in our cars and in our phones and in our watches. We like to know what the weather's going to be tomorrow. We like to be able to communicate all over the world. We like to be able to keep track of what other folks are doing. So us and other nations around the world have been launching satellites continuously since the late 1950s. And it's getting more and more and more as the satellites are necessary for more things like communication. So the number of satellites, as you saw, is exponentially growing nowadays. So the why is because we like our technology nowadays. But similar to taking care of the atmosphere here on Earth, we got to take care of the area that's just beyond our atmosphere out in space as well. And so I think the nations are kind of starting now, as you can see, because the first deorbit missions are not happening until next year, and it's the ESA that's doing it right now, not NASA. So it will be a while before that technology gets really, really good. Yes. Oh, I'm sorry. Yeah, everything, it falls down. It falls down. So yeah, there's stuff up there, but it's the same as, you know, like smoke from your fireplace. So eventually it will, it will come down. Did you have a question over here? Because it's tough to see it with the light there. Yep. Yes.
Getting this space debris running into it is a difficult concept to grasp. Let's say everybody is at 250 kilometers like this. The stuff that's hitting objects that are in this orbit is coming from above. In other words, it's got no propulsion system to keep it in orbit, and it's falling, and it's just a coincidental type thing. Am I right?
But when you did have, like, you know, like that explosion of, you know, with the anti-satellite test and everything, it did eject stuff out to further orbits as well. So you do get stuff coming from potentially all directions. But as you saw, you know, when I was talking about it, so I said that in general, the objects up there in space are going about 7 to 8 kilometers per second. The average impact was 10 kilometers per second, and the max that you could get was 15 to 16. So you're not getting the collisions like this. You're getting them like this. So you are getting collisions that are coming from behind or off the side for the most part, but you're still getting head-on stuff as well. So,
Even though everybody's in the same orbit, you have to...
Not everybody's not in the same orbit. Everybody's not in the same orbit. If you looked at that, you know, the way to see that is you can go on to the Orbital Debris Program Office, and that video that I had up here that shows all the satellites going around the Earth, that's on there as well, and you'll see the satellites are going all different directions. But generally in that situation, they're at different altitudes. But you got to remember that when we launch satellites up, they don't necessarily stay at that altitude. They'll decay. The International Space Station constantly is kind of lowering back down towards Earth, and it needs to be boosted up. So that happens with our other satellites as well. The satellites from Starlink are all such that they kind of decay down over time as well, and they need to launch more up. So
these things are at different inclinations, and they're going around the Earth. One's like this, and another one's like.
You could have one in a polar orbit. You could have one in a circular orbit. You could have, you know, all sorts of different all sorts of different orbits. In general, because of the rotation of the Earth, most everything's going the same direction.
Thank you.
Okie doke. Was there any last questions? Yeah.
Little different subject. There's only one docking place on the international.
There's multiple. There's multiple docking stations. In fact, we how many craft are docked? They're going to run into a problem here very soon because the Boeing spacecraft is still attached, but there's multiple docking stations because they've got Progress, Dragon, Soyuz spacecraft, etc., all attached right now. Sorry, keep going with your question though.
So the question is, how are you going to get those people back? They can send another one up to another.
So your question is the Boeing Starliner astronauts. So which the issue right now, because it's a kind of it's a thing for us to keep track of. So they launched up almost 2 months ago now, 2 astronauts in a Boeing Starliner spacecraft. The Starliner is supposed to land out here at White Sands Space Harbor within view of the museum. In any case, they ran into issues with with helium leaks and then thruster issues, which the testing for all of that to try and figure out the problems is being done over, guess where? White Sands Test Facility. In any case, though, so those two astronauts came up in the Boeing Starliner spacecraft. They can't come back in another spacecraft right now because there's not spacesuits for them for another spacecraft. Say a Soyuz spacecraft where you got to be wearing a Sokol spacesuit to come back in that one, or a Dragon spacecraft where you have to be wearing one of SpaceX's spacesuits. They have Boeing spacesuits. So in any case, NASA's kind of got two choices. Well, not NASA really, it's Boeing, but it is NASA as well because there are NASA astronauts there. So they're working very closely right now. They either have to figure out everything and understand that spacecraft and figure out that it is safe to bring them back down. And they are trying to do that fervently right now. Or the other option is the astronauts just stay up there, not forever. So until they can send up another spacecraft with spacesuits for them to be able to come back in that spacecraft as a rescue type mission. So which will happen? What's my prediction? I got no idea. I know kind of what's going on with the testing. I know somewhat of what they've found out with the testing. And one of the issues is that when they had manual control of the thrusters, they were overheating. And they were overheating because of essentially the thermal shielding around them. It was causing radiation coming back in, overheating the thrusters. The thrusters were shutting down. Okay, if enough of your thrusters shut down when you're on re-entry, that's a bad day. So they need to make sure that that cannot happen coming back in. Eventually, though, you run into a problem with the battery on that spacecraft. They've already extended the mission beyond what's the nominal battery life. They know that there's a certain factor in there, so it's already extended beyond that. But there is a certain point when you say, no, it's not safe anymore to bring them back because of potential battery issues as well, helium amounts on board for the maneuvering engines, etc. So what is going to happen? Like I said, I don't know. No. Nope, no, it's all internal to or external to the spacecraft, and anything done with that would have to have been done in the design phase and the installation phase. So yeah, yep. Yeah, it's not like a 75, or a 65 Mustang where you could just, pop something in and out. So it's crazy complicated. So, okie doke. Thank you so much for joining us for the Launchpad lecture today.